This is Mr. Craig, and this is day 128, topic 11, Electrochemistry, Part C. And today I want to talk about non-spontaneous electrochemical reactions. And what I have at the beginning here is voltage and equilibrium. The bad news is you're not going to do very much or see very much on the AP exam dealing with that. So I'm not going to get too concerned, and you're really not going to see any problems over that. But I do want to make you aware of that equation in case you do happen to come across it later on once you get out of AP Chemistry. Do realize that the log of K, and this is a little bit of a rearrangement of the Nernst equation that we worked with earlier in this topic, and that when we deal with equilibrium, and we don't do a whole lot with the electrochemical system here, but again, remember that E is positive and K is greater than 1, and the forward reaction is favored. What that means is the reactants will form the products. So we've been saying that all along, that if anything is spontaneous, then the reactants form the products. Therefore, delta G would have a negative sign, and the K obviously would be greater than 1 because, again, products over reactants. Therefore, if our K, or our energy, I'm sorry, not our energy, our voltage has a negative sign, then the reverse direction is more favored, the products forming the reactants. Again, we're not going to work with any equations dealing with this, but I do want to make you aware of that. Electrolysis deals with the non-spontaneous reaction. So whenever we talk about an electrolysis reaction, we're talking about something that is not going to happen on its own. So we require work, we require energy to put into the system to make this take place. We will still have an oxidation reaction, we will still have a reduction reaction, however, it is not spontaneous. Watching the following clip will help explain with the electrolysis of water. Here is my demo for the electrolysis of water. Now, do remember that we talked earlier about electrolysis being a non-spontaneous reaction. And you'll notice that if you look at the electrodes, that there's nothing happening within this beaker with the two test tubes. And what I've got set up here is I've got my power source, which in this case is a battery, which gives us more than enough voltage that we need to make this reaction take place. I have two test tubes, and they're filled up with this solution that's mainly made up of water, but it does have some ions within it so that it can help conduct the electricity from the negative end to the positive end and then back to the battery. Even though that an electrolysis reaction is not spontaneous, we can, by showing the two test tubes, that there is a oxidation reaction and there's also a reduction reaction. And as you sit here and stare at this thing, or been staring at this device for the last minute or so, you'll notice that nothing has happened. Well, when I go ahead and connect this, and again, what I'm going to do is I'm going to connect the positive end of the battery to this electrode, and then I'm going to connect the negative component of this to the battery. And as soon as that the connection is made, you'll notice that there's some bubbling taking place in both of these test tubes. Now, the reason why I have the test tubes is so I can collect the gas. And in this electrolysis process, I'm actually decomposing water. I'm actually forming hydrogen gas in one of these test tubes, and I'm forming oxygen gas in the other. Also, what's taking place here, and again, the whole purpose of the ions in this solution is to allow for the electrons to move from one chamber to the other. In other words, if I were to feel this, yeah, I can't personally feel that there's an electrical charge here, but it's obvious that the electrons are being transferred from one side to the other. Now, in one of these, there is an oxidation reaction taking place, and in the other, there's a reduction. It's very, very difficult to sit here and to analyze and differentiate between which is being oxidized and which is being reduced. Also, when we look at this, you'll notice that the rate of formation, in other words, this test tube here on the right appears to be more cloudy than the test tube on the right, or I'm sorry, on the left here. And what you'll notice is that actually this is a lot more reactive than this. In other words, this one is forming the gas a lot quicker than this test tube. And actually, even though it may or may not appear that way, it's a doubling. So the rate of formation is actually twice as much. Now, let me see if I can zoom in on this without disrupting how that is actually generating that gas. Now, based on stoichiometry plus the other reaction, the oxidation reaction, the reduction reaction, we can look at this and determine which is which. From our standard reduction potential sheet, here are my two half reactions that I have. In this case, the oxygen is being oxidized, and based on our standard reduction potential sheet, which is a reduction reaction, it does have a positive 1.23 voltage. However, since it's oxidized, we flip the sign because we flipped the equation. On our standard reduction potential sheet, we have water that decomposes and forms hydrogen gas, and that's on the lower end of the standard reduction potential sheet, and that has a negative 0.83 voltage. Now, what's nice about this is it actually shows our overall balanced equation that the water molecules do break down and form oxygen gas and hydrogen gas. What's also very nice is it's creating ions to help allow for that passage of the electrons or charges. Now, whenever hydrogen comes in contact with hydroxide, what happens? That's right, it forms water. So the solution's not going to become more acidic or more basic. It does for a moment and in the respective test tubes, but as soon as these ions come out of the test tube and come in contact with each other, they automatically form more water molecules. So when we look at the overall balanced equation that's taking place here, if we have four of these things that are actually forming water molecules, we can remove those out and now say that this is our overall balanced equation for the decomposition of water, is that we have two hydrogen molecules and one oxygen molecule that's being formed. So again, when these two come together, they form water molecules. Well, we have 6 total over here. 2 of these actual water molecules is being used to make hydrogen gas and oxygen gas. Now, this reaction's been going on for a few minutes here, and we can obviously see the difference in the height of the gas, or actually the amount of gas that's being produced. The temperatures are the same, and according to PV equals nRT, however many particles we have, if we had equal numbers of particles, that would occupy the same volume. So since from our balanced equation that we looked at earlier, where we had a 2-to-1 ratio for hydrogen to oxygen, this is exactly what we should expect, that we should have twice as much gas, and this is hydrogen gas, and this is oxygen gas. So we're actually producing pure hydrogen and pure oxygen, which is safe to release to the atmosphere. Looking at examples part 2, dealing with electroplating. Electroplating is a process that's an industrial process that helps put very attractive metals on cheaper metals. In other words, electroplating is used to make jewelry, silverware that looks like it's made out of pure silver, but again, some of these metals are so soft that they have to have a stronger metal as an undercoating, and then they'll cover it with some metal. And electroplating is this process, and we'll have some problems that will be associated with the electroplating. But do realize that it's a non-spontaneous action. We use electrolysis to take the ions out of solution and actually plate it or place it onto this cheaper metal. If you've ever seen chrome bumpers, and this is mainly on older cars, or anything that's done with chrome, it's an electroplating process. It's very, very cool, and it's very, very fast. So we'll take a look at those types of calculations here. The equation that we want to use for electroplating is this equation right here, which is also on your equation sheet. Actually, let's go ahead and find it on the equation sheet. It's found on the oxidation reduction portion of your equation sheet, and again, it's on the back side The I here, if you're not real sure, it has it in the legend. This is your current, which is in amps or amperes. The Q here is not heat, it is not equilibrium, but it is charge, which is in coulombs. And again, we talked about what the unit for a coulomb is. It's actually a joule per volt. However, it's different with these types of equations. We'll talk about that in a moment. And then at the bottom here we have T, which is time, and that is in seconds. Okay, so there's your equation. So what we're going to do is we're going to do some calculations with this. We have our three examples, and let me walk through the steps for our first example here. Now, I've already worked it out for you on the example sheets. The question says, example number 1, 10 amps of current is placed through an electrolytic cell filled with molten lithium chloride. Now again, molten lithium chloride means that we have our ions there. For 500 seconds, how many grams of lithium are collected on the cathode? Now again, cathode is the side of reduction, and so we're taking an ion and we're actually placing it on the actual metal, so the cathode. So we talked earlier about the buildup of mass on the cathode. Same thing's taking place here. And again, this is not a spontaneous action, so we have to put work into this, and do recognize that the voltage, if you were to look at the voltage on the standard reduction potential sheet, is negative 3.05. So lithium ions do not want to form a solid on their own. Lithium wants to give away the electrons and turn into an ion. So the first thing that we have to look at is determine the amount of charge in coulomb that passes through the cell. So we were given 10 amps and we were given 500 seconds. So based on how many amps and seconds, that will give us our number of coulombs. Now if you want to leave it as an amp second, nothing wrong with that. So then what we're going to do is we're going to use Faraday's constant to get rid of the unit coulombs and change it into the number of moles of electrons that are actually being consumed or used in the reduction process. So we have 5,000 coulombs, and do remember Faraday's constant is 96,500 coulombs per mole of electrons. So that'll tell us that that's how many moles of electrons we have. And after we know how many moles of electrons we have, well, we have to find out how many moles of lithium is actually used. So there's our moles of electron, and for every one ion of lithium, it requires one electron to change that ion into a solid or into an atom. So we now found out how many moles of lithium we need, but the question wants to know what is the mass. So we're going to take the moles and convert it into grams. And so here's our final answer. So we would need 0.36 grams of lithium that would plate out in 500 seconds using 10 amps. Looking at example number 2, it asks, how long in minutes must a current of 5 amps be applied to a solution of silver ions to produce 10.5 grams of silver metal? So here's what we probably should do first. Well, we have silver, and we need to know how many electrons it takes to go from silver ions to silver metal. And I would highly recommend that you show this half reaction each and every time before you begin. So it looks like it's going to require 1 electron for every single one of the silver atoms. Okay? Now the question wants to know what time or how much time it would take. We're given 5 amps and we're given 10.5 grams of silver. Probably the first thing that we want to do is we want to find out exactly, how many coulombs it's going to take to get the 10.5 grams of silver. So we're going to start with our mass of silver. And silver that's a solid versus silver that's an ion still has the same mass. 1 electron is missing. No big deal there. So 10.5 grams, and we're going to change that into moles. So 1 mole of silver, which has a molar mass of 107.87 grams. Now once we have our number of moles of silver, we want to find out how many electrons are actually needed to produce this 10.5 grams of silver. So for every 1 mole of silver, or silver ions, however you want to phrase that, we need 1 mole of electrons. Okay? And then we get to use Faraday's constant because that's how we're going to acquire our coulombs. So at the bottom of Faraday's constant, which is 96,500 coulombs, or amp seconds, for every mole of electrons. Okay. When we type that in, we get a value of 9,393.25 amp seconds. Okay, so I have this unit amp seconds or coulombs. I don't care which way you go with that. The equation is given on your sheet is I over Q T. The I represents the current, which is in amperes. The Q represents the charge, which we just found, in coulombs or amp seconds, and the T represents the time. So what we need to do is we need to rearrange this to find out what the time is. So I'm going to have time and the charge switch. So now I have this equation where time is equal to Q over I. Okay. And then I can plug in my 9,393.25 amp seconds over my total charge, which was 5 amps. What happens to the units there? The amps cancel. You're left with time, which is in seconds, which is 1,078.65 seconds. And then we need to convert that into minutes. So I'm going to do that up here. So converting that into minutes, I'm going to take 1,878.65 seconds. And there are 60 seconds in every minute. And that equals 31.3 minutes. Okay? Again, not too difficult. There are multiple steps here, so you have to pay attention to what you're doing there. All right, let's look at example number 3. Example number 3 says, if 3 amps of current is passed through an electrolytic cell containing a concentrated copper sulfate solution for 2 hours, how many grams of copper metal can be collected or plated on the cathode? All right, so now we're given our 3 amps. Okay. And again, that equals our I. We're given 2 hours. And probably should change that into 60 minutes and 60 seconds. So get our seconds here. So that is 7,200 seconds. Okay. And the question wants to know how many grams of copper metal. Okay. So that's the information that's given to us. Scoot that up a little bit. All right, so we're also told that we have copper sulfate in our solution. So the copper, in this case, has a +2 charge because the sulfate has a -2. So we really want to focus on the copper +2, gaining 2 electrons to make copper metal. Okay, so there's something that's very important that we're going to use here momentarily. All right. So now the first thing that we should do is we don't know our coulombs, and we need to find out our coulombs before we can find out what our mass is. So our equation again is I equals QT, and again, don't mistake the Q. Look at the legend if you're not 100% sure. And we're going to rearrange. I'm going to put the time up here with the amps. So now I've got IT with Q, and I have 3 amps times my time, which is 7,200 seconds. So my Q is, what is that, 21 something? 21,600 amp seconds, or coulombs. Doesn't matter which way you go on that. Okay. So now that we have our coulombs, now we work backward from the last problem that we just worked, where we have 21,600 amp seconds, or coulombs. I don't care which way you go on that. We're going to use Faraday's constant to change our coulombs or amp seconds into moles of electrons. So 96,500 amp seconds for every mole of electrons that we have. From our balanced equation that we had there, from up above here, we had 2 electrons. So 2 moles of electrons for every 1 mole of copper. And then the last step is convert the moles into grams. And the molar mass for copper is 63.55 grams. And that equals 7.11 grams. Okay. So again, there's some multiple steps involved with this type of problem. Hopefully, it's not too difficult. The hardest part of this whole process or these types of problems is to make sure that we keep our units in check, we keep our variables in check, make sure that you're looking at your standard reduction potential sheet to find out how many electrons you have, make sure you're looking at the correct side of your equation sheet